Hello and welcome to Otten Math. In this edition of Otten Math, we're going to do some practice problems involved in graphing inequalities. The first problem, we're asked to graph the solution set of each system of inequalities. First is y is less than x squared plus 8. The other is y is greater than negative x plus 12. The first thing we want to do whenever graphing inequalities is to write the form of the figure as though the inequality was not there. So we change the inequality to an equality. So in this case we have y is equal to x squared plus 8, which is our parabola with a vertex at 0, 8. And then y is equal to negative x plus 12, which is our line with a slope of negative 1 and a y-intercept of 12. Next thing we want to do is we want to write a solid or dashed line. We write a solid line when we have a greater than and equal to or less than or equal to. We write a dashed when we have just greater than or less than. It's solid because when it's greater than or equal to, the line is part of the solution of the system of inequalities. When it's dashed, the line is not part of the solution. Alright, so I have y is less than x squared plus 8. After we draw our line, or our figure, and graph it, now we're going to test a point that's not on that line or not on the figure. I always like to test the point 0, 0. So I test the point 0, 0 for y and x squared plus 8, the parabola, and I get 0 is less than 0 plus 8. Now that's a true statement. So I'm going to graph everything that is below the parabola. Because if 0 is less than x squared plus 8, then I know that everything below it is going to be, or is going to satisfy the inequality. Okay? Next thing I want to do is I want to apply the same principle. I'm going to put in a point that's not on the line, and I'm going to ask whether or not it's true. Next one says y is greater than negative x plus 12. So if I plug in the point 0, 0, I have 0 is greater than 12. Now I know that that is not true. So I know that 0, 0 is not part of the solution. So what is part of the solution is on the opposite side of the line. So I graph in what's on the opposite side of the line. And my solution becomes, and it's difficult to see in this particular graph, everything that is in common for both solution sets, or both inequalities. So I have this area that's going to be part of the solution, and then this area up here, which will be part of the solution. In the next problem, similar problem, we have to graph the solution set of each system of inequalities. We have x squared plus y squared is less than or equal to 25, and y is greater than or equal to the absolute value of x. So we graph x squared plus y squared is equal to 25, and we end up with this circle here. A circle with a center at 0, 0 and a radius of 5. And then we graph y is equal to the absolute value of x. It looks like this V shape here with its vertex at the origin. Now we said before that if it's less than or equal to or greater than or equal to, then the lines are going to be solid. So I have a solid line for a circle and a solid line for this graph of y is equal to the absolute value of x, because the lines themselves will be part of the solution. Next I test a point that's not on the line. And in this case we'll do it for the circle first. And I'm going to test the point 0, 0. So if I have 0 plus 0 is less than 25, I know that that's true. So 0 plus 0 is less than 25. So what I'm going to do is I'm going to shade in the area now inside of the circle. Remember, our solution is the shaded area, the area that's shaded and commonly shaded to both inequalities. Next I test my point 0 is greater than or equal to the absolute value of 0. Well, it's a problem to test that point because that point is actually on the line. So let's test another point. Let's test a point 0 for x and 3 for y. So 0 is greater than, 0 is going to be less than 3. And that's a true statement. So we just tested the point 0, 3. So 3 is greater than 0. So that's true. So we know that everything inside of this V-shaped object is going to satisfy that inequality. So we end up with what's common to both, this pie-shaped piece that's inside the circle and somewhat inside, or definitely inside, but not all of the value inside of this graph of the inequality of y is greater than or equal to the absolute value of x. In the third part of this problem, we have yet another requirement to graph the solution set of each system of inequalities. First, we graph y is, x times y is less than 12, and we have these two shapes here, and they should be dashed. And we have x squared plus y squared is less than or equal to 16. And in this case, we're going to have a solid circle. So let's just complete dashing these lines. All right, so we want to test our point. In this case, I want to test y and x at 0 because it's not on either line. And I have 0 times 0 is less than 12. So I know that that's true. So I'm going to shade in everything between these two lines. And then I have x squared plus y squared is less than or equal to 16. And again, I'm going to test my point 0, 0. I have 0 plus 0 is less than or equal to 16. So I can see if I graph that, I'm going to have everything inside of this circle, and also e equal to the circle. So my solution set is everything inside and on the circle itself. Okay, moving on to the next problem. This one's a little bit more complicated than the other two, or the other three. This one asks us to graph the solution set of the inequality absolute value of x plus the absolute value of y is less than or equal to 4. So we want to rewrite these equations without the absolute value signs. Well, how do we do that? Well, let's think about this conceptually. If x and y are both positive, then it doesn't matter. We just take off the absolute value signs. We have x plus y is less than or equal to 4. If they're both negative, then we know that x plus y, negative x plus negative y, must be greater than or equal to negative 4. Third case is if we have a positive value for x and a negative value for y. We take off the absolute value signs. We're going to have to change the sign of the y value. So we write in x minus y is less than or equal to 4. And the last one is the case where we have a negative value for x and a positive value for y. So we have to reverse the sign of the x value and then add the y value. It's going to be less than or equal to 4. Okay, so now we have our four inequalities as I rewrite them just in terms of y. Y is less than or equal to negative x plus 4. That's our blue line. Y is greater than or equal to negative x minus 4. That's our black line. Y is greater than x minus 4. That's our green line. And y is less than or equal to x plus 4. That's our red line. So we test a point, again, not on the lines, and I'm going to test a point 0, 0. And as we do that, we're going to find out that 0, 0 is true. It's going to hold true for each of the inequalities. So 0 is less than 4. That's true. 0 is greater than negative 4. That's true. 0 is greater than negative 4 again for the third equation. That's true. And 0 is less than 4. That's true as well. So I'm left with a shaded region. That's everything inside of this diamond shaped figure, inclusive of the lines, because again we see less than or equal to, greater than or equal to. The lines are included as part of the solution. Okay, in the final problem, we're asked to approximate the area between y is equal to 0 and y is equal to x squared between x is equal to between x is equal to 0 and x is equal to 3. So we just rewrite that as x is equal to 0 or between 0 and 3. So this is moving us more into calculus, or the beginnings of calculus. And what we're going to do is we're going to block off each of these pieces into trapezoids or triangles in order to figure out what the area is for each of these individual pieces. So let's start with the first one. So number 1 is going to be this area here between 0 and 1. And we're going to use the equation for a trapezoid. So number 1, we have 1/2 of base 1 plus base 2 times the height. Right, so that's the formula for the area of a trapezoid. 1/2 of base 1, which we'll say is 1. Base 2 is going to be 0 times the height, which is going to be this horizontal distance here, because the trapezoid's turned on its side, so to speak. So I've got 1/2 of base 1, which is 1, plus 0 times the height of 1, which gives me 0.5. Number 2, we use that same equation. I've got 1/2, now this is base 1 is 4. 1/2 of 4 plus base 2, which is now 1. That was our base 1 before. Times 1 again, and it's always going to be a height of 1. And this is equal to 4 plus 5 is 5 divided by 2. I have 2.5. And I have my last trapezoid. I have a base 1 of 9. So 1/2 of 9 plus base 2, which is this line here, of 4, times the height of 1, which gives me 1/2 of 13, which is equal to 6.5. So if I add all these together, I approximate the area under the curve as 9.5 units squared. In actuality, if we do the work, we'll find that the value of the area is going to be equal to 9.